Everyone, hope you're doing all right. You should be watching this only after you feel comfortable with equilibrium, all right? It's going to be tough. You're probably going to have to watch it more than once. That's fine. I didn't learn organic the first time around or the second time, all right? It'll be okay, I promise. So you should remember that equilibrium is kind of like the chemistry version of homeostasis. We can figure out how reactions are going to return to equilibrium once we disrupt them by Le Chatelier's principles. Some French dude. So you should remember from biology, living environment, that homeostasis is your balance. So when you are cold, your body will shiver to get all of your muscles moving and warm you up. When you're hot, you're going to sweat to cool your body off. Le Chatelier's principles, if we mess up equilibrium, his rules get us back. It's a little bit different with equilibrium in chemistry than it is in biology. I'm trying to move the bubble. Okay, there's the bubble. Okay, so there are a few ways that we can disturb equilibrium. The first is that we change the amount of stuff, which in chemistry, the science word for that would be to change our concentration. We can add stuff or take stuff out to change concentration. We can also change the temperature. So if you take a reaction and put it in the refrigerator, now it's a colder reaction that can disrupt the equilibrium. It's kind of like the equilibrium of your body. And then we also have, if and only if we have a reaction that involves gases, if we change the pressure of that reaction, we change its happy place, then we can, again, disrupt equilibrium. So, here we go. I'm sorry if you're scared. Go back and watch the equilibrium video. Make sure that you are 100% good with that before doing this, because I'm about to blow your mind, all right? So, there is a general rule that we can use to figure out how our equilibrium is going to get back. Okay, so our equilibrium is going to shift. Remember, we can read these. Oh, wait, I want the pointer. My camera is right here, and I need to see something behind the camera. I propped it up on a box of tissues because this is professional. Let's see, where's my pointer? You like my top? St. Patrick's Day. Here's my pointer. Okay, so we can read these reactions both forwards and backwards. So here we go. Let's use this little jingle, add away, take towards, for changing the concentration. Let's say that I added a bunch of nitrogen, okay? So I was supposed to have just 1 mole of nitrogen, which would be represented by just one set of pink circles. My blender's going upstairs. Do you hear it? Welcome to online teaching. So I have added extra nitrogen here, and now my reaction is not balanced, right? Because here I have 6 nitrogens on this side, but only 2 over here. So my reaction is going to try to get balanced. And when I do that, what's really going to happen is that these nitrogens are going to break apart and start making more ammonia to try to shift the reaction so that it gets back to normal. So again, you're cold, your body shivers to warm you up and get you back to normal. In this case, if I add a bunch of nitrogen, my reaction has too much nitrogen and will start to break it apart and shift away from the nitrogen. So that's the add away. Add a bunch of nitrogen, the reaction is going to shift away from the nitrogen. So I would say that this reaction shifts right. You have to know your left and right here, okay? Remember, left is, this is a mirror image, but left is the one that makes an L, okay? If we're going this way, this would be my left, but it looks backwards because this is a mirror image. Okay, so there we go. Add nitrogen. The reaction is going to shift away from the nitrogen and towards the ammonia to try to maintain and get the balance back, okay? Good so far? I hope so. I can't hear you. Now, let's say I did the opposite. Let's say I took a bunch of nitrogen out of this reaction. Now I have no nitrogen at all, and this reaction, not in balance. It is not happy. So these ammonias over here, the NH3s, they'll start breaking apart to bring the nitrogen back to get the balance back. So this is take towards. If I take out the nitrogen, the reaction will shift toward nitrogen to get more of it. I hope this is making sense. Please leave comments if it's not making sense, because I want it to make sense. So it would take nitrogen out. The reaction is going to shift toward the nitrogen to make more of it, which means we would wind up with less ammonia. This stuff would break apart. Yes, by default, we would get more hydrogen, but we're not really too concerned about that. It'll just kind of bounce back and forth until it's balanced again. Okay, next we can change pressure. And I think this one might be a little bit tougher. So there's a lot of words here. This is essentially how it goes. If the pressure is changed, the equilibrium is going to shift to try to get the pressure as back to normal as possible. So if you look at this reaction down here, the reactants in total have 4 moles of gas. The nitrogen has an imaginary 1 plus the 3 for hydrogen gives us 4 in total. See? Okay. And then the ammonia over here, I just have 2 moles. So the reactants take up more space than the products because 4 is bigger than 2. Again, the reactants take up more space. That's volume. So if my reactants have a bigger volume, that means that they are going to be under more pressure. So let's say that I have this reaction happening in a coffee can or some other sealed reaction vessel, and I just pump a bunch of helium in there. I just fill it up with helium. Helium is a noble gas, and it's not going to react with anything inside my coffee can reaction vessel. So what happens is adding all of that helium is going to squeeze everything. It's like putting, pumping air into anything. It increases the pressure. If you pump air into a bicycle tire, the bicycle tire gets tighter, like it's less squishy. That's because there's a lot of air in there. It's building up pressure. If I add a bunch of helium to this reaction vessel, it's going to feel squished because the helium's taking up space, right? And the helium is not going to react with anybody. So when that happens, when I increase the pressure and I squeeze my reaction, these 4 moles are not happy. They go, ugh, it's so tight in here. I can't manage it. So what happens is the forward reaction is going to be a little bit faster. So this reaction will shift right to make more ammonia to alleviate the pressure, because the ammonia is going to shrink basically because it's 2 moles as opposed to 4. I hope this is making sense. When you increase the pressure, you wind up squeezing this reaction really, really tight. And when it gets squeezed really tight, the side with fewer moles is going to be happiest. Again. Higher pressure is going to shift to something with less moles to alleviate that pressure. Now, the opposite is also true. If I took my reaction and then I gave it extra space, I gave it more volume, which means my pressure goes down, it is going to shift to the side with more moles of gas to bring the pressure back. This, I think, is one of the things that you just learn with practice. I hope this is okay. This is going to be one of the hardest lessons that you learn this year, okay? It just sucks that we're not doing this together in person. Okay, next. Next, please. Next is temperature. Now, temperature is going to be a little bit tough. It's going to depend on whether your reaction is endothermic or exothermic, okay? So, ignore this text for now. We're just going to focus on this reaction. So, the Haber process, which is this reaction here, that has a negative delta H. You should know by now that a negative delta H is an exothermic reaction. It's getting rid of heat. Now, would this reaction be happier in a refrigerator or in an oven? It's trying to get rid of heat. Okay? If I'm trying to get rid of heat, then the reaction, if I put it in the refrigerator and lowered the temperature, this reaction would be happier from left to right. Okay, so if I decrease the temperature, this thing is going to shift to the right. it's going to shift towards my products. If I took this reaction and I put it in an oven, or I increased the temperature, this reaction is trying to get rid of heat. So if I give it more heat, it's like, ugh, what are you doing? Go the other way. So what that means is that this reaction is literally going to go the other way. It's going to go backwards, because remember, the exothermic graph is the mirror image of the endothermic graph. If you're not sure, go back to 10.2 in your notes and flip it open and look at the two graphs. They're mirror images of each other. If I wanted to flip this reaction and read it backwards, then I would have an endothermic, and this would be positive. Okay? So I can't just tell you the temperature is going to shift to the left or to the right. I can just tell you that if it's exothermic, it likes to be put in a cold place, because when it's cold, you can get rid of heat faster, right? Because heat flows from high to low. So if I'm hot but the room is cold, my heat is going to leave me very quickly. Same thing here. So this reaction is trying to get rid of heat. If I put it in the refrigerator, it would be happiest. I think that's all I had for you. It is. So that means I need to wake up the dog, because I promised that you'd be able to see the dog. Koopy, come here. The kids want to see you. Ouch. Come here. Are you tall enough? Oh, he's not tall enough. There he is. Hi. Hi, the kids wanted to see you. You say hi to the kids? You say hi to the kids? Hi. You say, hey guys, I'm just sleeping all day. And then when I'm not sleeping, I'm crying. And it's time for me to go back to my nap. Okay. Now I have to give him a treat because I just woke him up. Okay, so if you were unclear of the video, go back, watch it again. If you already watched it a second time, leave a comment, leave a question. I will be happy to get back to you, and that's it. Good luck. If you can understand Le Chatelier's principles, you're a rock star. And if it takes you a few tries to understand it, then you're normal, because this stuff is hard. It's very hard. All right. So best of luck. Love you all. Hope to see you soon.